module, which is called IP1. It's called IP1 because there will be an IP2. This has a little image on the cover page, and this image is trying to illustrate what is the why of what IP is doing. IP is the global interconnection layer, so it's meant to interconnect the whole world together, which was the intention when it was developed. As we will see, there was still a bug in this intention, in the space of the addressing space, the size of the addressing space. We'll see that in a second. Here is a table of content. I apologize for those of you who are extremely well organized and downloaded the PDF before the course. I changed the order of sections 4 and 5, but that's the only change. If you have downloaded the old version, it's the same, just the order has changed. Because I'm not sure I will finish section 5 today, and we need section 4 for the lab. So we'll have changed the order. Otherwise, no change in the file. We will see IP. IP is very, very simple, but it's very important. That's how the internet is built. It's perhaps not how the internet is visible. We use applications, we use the web, YouTube, Facebook, etc., email. But all of this exists because there is IP. There is IP unicast, which is practically all IP traffic today. There is also IP multicast that we will discuss a bit later. IP multicast is very special, very different from everything else, and is used in industrial networks and in special cases like Swisscom TV distribution, a few special things that we will discuss a bit later. So today, what we call is unicast. Unicast means I'm sending data to one destination, not to 1 million destinations at the same time. IP follows two principles. When I say follow, again, those are the principles that, in principle, any IP system should obey. But of course, you don't go to jail if you make a system that don't obey this system. Also, you're not breaking a law of physics if you make a system that don't obey these rules. So these deviations will exist, of course. Nonetheless, most systems in the internet obey to these rules. What are the rules? The first one is longest prefix match and structured addresses. Recall that the goal of IP is to interconnect local area networks. This is how it was originally done. At the origin, when IP was developed, it was possible to communicate inside a campus by the MAC layer only, by Ethernet only, because a campus had one big computer, in my case. Other campuses had perhaps 2, 3, 4, 5 computers, and then they slowly grow to a few tens. So local area network was sufficient for things to work. And then at that time, there were zillions of different protocols that work directly on those MAC layers. So you could transfer a file from, or an email, using things that were special to the local environment where you were in. And the goal of IP was to interconnect all those systems together. So it was an interconnection means. And the way it did it was to first allocate addresses that reflect on which campus you are. EPFL had 128.178 dot something, IBM had 9 dot something, etc. So you allocate to every network a prefix, and then the interconnection will be made because we know the structure of the address. However, sorry, I should say. In addition, a few smaller details. The address is not the address of a machine, like other protocols do, but is the address of an interface. That's a design choice. It could have been done differently, and there are other networking protocols that use different rules, but that's the design choice. In particular, this machine here that has, can have Ethernet over its USB port, also has Wi-Fi. Then it has 2 IP addresses when it has both interfaces active. The IP address is structured to reflect where the system is in the world. That's reminiscence of when it was designed, if we would design IP today, probably we would not do this, because this was done at a period where mobility did not exist. I mean, computers were not mobile. In mobile computers, you needed a little cart like this one to carry it. So there was no concept of mobility. You would stuck a computer somewhere, and they did not think that we would have this in our smartphone. When you are mobile, of course, you're moving all the time, so your IP address that should reflect where you are has to change all the time, which is what happens with mobility today, which is a major pain, but this is a consequence of this. As we mentioned, every packet should contain the IP address of the destination, and every system, in particular every intermediate system, should have a table to know where to send information. And this table should do longest prefix match. What does longest prefix match mean? Well, it's illustrated on this figure here. Here I'm showing a very, very stylized version of what we see in computers, what you see in the lab. I'm showing here, for example, a computer, Lisa's computer, that has an IP address A.H1. Doesn't mean it's literally A, but it means the subnet, for example, is A, and the host part is H1, for example. And then there are 4 routers. The routers have, like the hosts, but mainly the routers have what is called forwarding table. Forwarding table is also called routing table. Those are synonyms. The routing table or the forwarding table indicate what to do with the packet by following a number of rules. And if we look, for example, at router R2, it says anything that starts with capital A here stands for a number of bits of the IP destination address, should go to output number 1, which is here. Anything that starts with B should go to number 3, and everything that starts with B followed by D should go to number 2. So here we see that the prefixes are not just a network part and a host part, but inside the network part there might be prefixes of prefixes. For example, at EPFL, all IP addresses, to simplify, start with 128.178. But this is not the network part. When you are in a given place of EPFL, your network part is 24 bits, so it's, for example, 128.178.156. So there might be rules that say anything that starts with 128.178.156 go in a given corner, but in other places of the internet, you're not interested in knowing whether this destination address is in this auditorium or is somewhere else inside EPFL. For example, if you're a router in the US, the only thing you care is to send it towards Switzerland or towards EPFL. So such routers will have a prefix which is 128.178. They will not route the packet based on more information. And here we have a case where router R2 has, perhaps this is B is the EPFL prefix, B.D is a given subnet of EPFL, and this is all the rest of EPFL. So we have 2 rules that are overlapping. And when you have rules that are overlapping, the thing that comes together is called longest prefix match, that I'm illustrating here. When A.H1 sends a packet to this one, which has address B.D.H2, well, this router has 2 entries in its routing table that match, the second and the third. Out of those 2 entries that match, the second and the third, which are here, we break the tie by saying we choose the longest match. So the second line has more bits that match. There is B, but also D, compared to the third one that has only the B part that matches. Therefore, the third one is preferred. You send it to that one, which makes sense. It just means if you have more specific information, you use it. In contrast, if, well, that's it. If you would send, in contrast, a packet from A, for example, to BCH2, so if there would be a packet to send to BCH2, then, of course, it will go to interface 3 of router R2, and this will happen because when doing the match, there is only one single match. It will come here. Very important, but very powerful. And that's the first principle, and this is how we can have, for example, default routes by having relatively small routing table entries, we are able to aggregate a number of destinations. That's rule number one for the internet. Rule number two that we've seen already is within the same local area networks, don't use routers. If A and B, for example, W and P, when they communicate, they should not send the data to the router here. There's no reason to do that. You could imagine that you send everything to the router and the router knows for you. This is how you do for the post office. In principle, if you have a letter to send to somebody who lives in the same village as you, normally you still put it at the post office. Here, IP says, no, you don't do that. You go directly to the mailbox of that destination and send it to you. If you are on the same local area network. What does that mean, to be on the same local area network? It means something physical. It means that by manipulating MAC addresses, I am able to send the packet directly to the destination, to the MAC address of that destination. This is what it means physically, which means I am connected to the same Ethernet concentrator, or I am on the same Wi-Fi network here. So P and W are on the same network. When W sends something to the printer, the router will see nothing. Logically, being on the same subnetwork is identified by looking at the subnet part. So we need the mask, and by analyzing P and W should have the same subnet part. That's a consequence of this rule. Okay, it's playing animation. Okay, let me continue with my toy questions. We observe a packet from W to P at point 1. Point 1 is this point here, on the wire between W and the Ethernet concentrator. Which IP destination address do we see? Yes? Which the? This device here. It's a Wi-Fi base station, which probably is not a router.
It's not a router, then the router is further. Every Wi-Fi access are connected to the router.
This is connected via Ethernet. So it's like in this scheme here, it's connected to a router via Ethernet, probably here in practice. Not by Wi-Fi, but via Ethernet.
You can also see a router and Wi-Fi access in the same device.
There could be, but we'll talk about that a bit later. There could be, but imagine there is not here. I close the poll. So we observe a packet from W to P. If there is an IP destination address, it should be, of course, the IP destination address of P. So 1 is a plausible answer. 2 does not make any sense, as we have seen. We send always to the IP destination address of the final host we want to reach. And we could ask the question, is there an IP destination address? And here, Well, in fact, both are possible depending on which protocol you use for printing. But today, in most reasonable cases, the correct answer will be number 1. If you use TCP-IP, the principle of TCP-IP is if you use TCP-IP, there is always IP, even if it's not needed because it's in the same local area network. So if you are in the field and you have a laptop and a printer, you're connected to nothing, and you just want to print from your laptop to the printer, you have no router that you're connected to, you will still have an IP layer. There are protocols that work without IP layer. There are called NetBIOS. The very old AppleTalk did it also without a network layer. It would recognize that the thing is on the same local area network and send it directly. But it's not a good programming design to say if I send data to the printer, depending on the IP address of the printer, I need to do something different. For example, if I have the same printer and now I put a router between me and the printer, the host software should not be impacted by that. So in practice, we see that, of course, if we use TCP/IP, there is always an IP header. Well, those are the two principles of IP. Now, we'll see a bit more details. And in particular, there are two versions of IP, Ipv4 and Ipv6, which you have already discovered in the lab. A bit of terminology. The terminology is not unique for lots of reasons, but primarily because this is done by software people. So when you write the doc of something, then nobody checks how you write it. So you have to live with the way it's written by different people. I will try to have a clear terminology for what I call the architecture. Architectures is the things, the rules that are defined by the Internet Engineering Task Force for the TCP/IP architecture. So those define very crisp and well-defined words. But many people use them differently. For example, many people say an IP for an IP address. Okay, everybody understands, so it's fine. It's like I give you my telephone. I'm not giving you my phone, I'm just giving you my telephone number. So the same kind of things are done. Router is, if we want to be formal, an intermediate system of the IP layer. An intermediate system means something that's in the middle. If you remember the slide I showed 2 minutes ago, we had two devices, and in the middle, the router. It's in the middle means it's receiving data that are not for itself. It's not the destination of the data. It's called an intermediate system. An intermediate system of the IP layer is something that receives data, sends them further downstream, and of the IP layer, it looks only at the IP header, which is practically only IP addresses. An intermediate system of the IP layer is traditionally called a router. However, it's very important to make the difference between a function and a box. Each of your computers can be a router. It's called enabling IP forwarding. If you have an Ethernet interface or a Wi-Fi interface and a cellular interface, you can do routing between the two, or between one Ethernet interface and Wi-Fi, or if you have several Ethernet interfaces, between the several Ethernet interfaces. So if you enable IP forwarding in your Windows or Mac or Linux computer, then your computer is functionally a router. But nobody would call it a router. You'd say it's a PC or a Mac, but functionally it's a router. Now, because all those functions can be implemented in zillions of very different ways, it's important to keep in mind the difference between function and the box. Somebody asked a question about what is this box doing? It's a Wi-Fi base station. Well, it's a Wi-Fi base station. I think, from what I know of EPFL, it is both a Wi-Fi base station and a bridge, which is an intermediate system of the MAC layer that we will discuss in 2 weeks. Some boxes like this also have a router inside, which means they just have a few thousand lines of code that does the IP forwarding algorithm and obeys the rules we've seen before. It's important, therefore, to remember the difference between what I call architecture, functions, and products. You can have products that do zillions of different things. Other terminology is a host versus a router. Host, in the context of a protocol, means the end system, the end of a communication path, not an intermediate system. But, as I said, host may mean very many different things. You find also terminology for intermediate systems that is called gateway. In 1975, a router was called a gateway. Now today a gateway is more an application layer intermediate system, but you find this when you want to tick the boxes in Windows. It says what is your default gateway. Default gateway means the default router. Okay, this is my clock. So we interrupt the lecture for 15 minutes and do a break. And the only non-obvious part about the addresses is how to translate the different formats. Here are Ipv4 addresses, which, as you know, are 32 bits and are typically given in this format here called dotted decimal. But you can write them in hexadecimal, so you have the exact translation from this to that. So 98, which is often read 98, is not 98, is in fact 152 if it's in hexa. You can write it in binary, which is what the computer does, but of course is very painful because there are many bits. It's important to be able to convert from binary to decimal and to hexadecimal. You all have calculators, so it's easy to do with a calculator, but it's worth knowing by heart a few conversions. For example, a string of 8 bits in binary means 255, which is 2 to the power 8 minus 1. And a string of 4 bits is 15 here. And in hexa is FF. F here and FF. We've seen this example already. Here are some of the EPFL addresses. They all start with 128.178 or 128.179, which means that the EPFL prefix is in fact 15 bits. The first 15 bits of this string identify EPFL. Routing tables have routing prefixes that need to be displayed also. For example, in the labs, when we will be analyzing what happens in a router, we need to be able to see what is the routing prefix. So the common notation is to use a slash by the number of bits. For example, if I look at this router, EDOSWI, which is a router that interfaces EPFL with the switch network. Switch is the internet service provider that is used by EPFL. Then it has, for example, those entries, 128.178.29/24, and it says where to go, a bit like in the previous slide I showed an output port. Typically on routers, this is not done by giving an output port on the box, but by giving the Ethernet, the physical interface that has to be used, and the destination of the next hop. So here, this routing table means when this router receives a packet that has destination 128.178.29 dot something, anything that starts with this prefix, should go to this machine. What is this machine? 102. This is this machine here. So it is saying, I am an entry point of EPFL, and then I know I am connected to 2 other routers via something which is the EPFL backbone here. And I know that whatever goes to 29 has to go here. So this router needs to have this information. It's not given by the IP protocol, it's given by the routing protocol that we will see a bit later. So we need an additional protocol between the routers to be able to discover how to go there. Then it has a second line that says 128.178/16 that goes to 103. 103 is this one. How should we interpret this? Well, this is a shorter prefix than this one, and in fact, this is all of the, let's say, EPFL network except the Wi-Fi part. So this, we can interpret that as a first level of default route. It means that if this router has a packet to forward and the destination is inside EPFL, in principle, two things can happen. Either it's in the .29 and it should go here. If it's not .29, for example, it's 128.178.30, what will happen? Then the only match will be this one, so it will go to this. In other words, this is the default route seen from this point to the whole of EPFL. And there's an exception. If we go to this part, we don't go to the default route. And then there's another entry, which is 0/0. That means 0 bit, means it's the empty entry. So any destination matches this one because it's empty. What does that, and it points to this 47.3, which is this machine here, the red circled machine here. What does that mean? Well, that's truly the default route. That means whatever packet I have, if it doesn't match any of those two, which means if it's not an EPFL packet, I send it towards the red box here, which means towards the rest of the internet. This is a typical behavior you have when you are an enterprise network that's connected via an internet service provider. You have table entries that correspond to the internal structure, and anything that is not inside your network, you send to the rest. You see that this longest prefix match rule in this a bit simplified example proves that with very, very few table entries, we're able to know where to route everything in the internet. Similarly, if we look at the red router here, it has one default route that goes towards the backbone of the switch network, and another route that says anything that's EPFL should go to this one here. You have certainly seen special addresses. There are in IPv4, like in IPv6, special addresses that correspond to different needs. There is the absence of address, which is typically 0. So 0 address means an invalid address. Why do we have an invalid address? In principle, we don't. But there might be cases where you have a field that's called an IPv4 address, and you don't know what to put in this field. And it's better to, a good programming practice is every variable should be initialized to something that you understand why it has this value. Don't let randomness initialize the thing for you. So here's the same. If for whatever reason you need an IP address and you don't know which address to put, you put 0. Then there is a very popular address called the loopback address. In IPv4, it's 127.0.0.anything. In practice, most people use .1. Loopback means it's the IP address of this machine seen from this machine. So any IP packet that has destination address, that one, will never get out of this machine. Why is that useful? If you have a server running on your own machine, exactly. It's useful for a variety of reasons, but perhaps the primary goal is for testing. You're developing a server program, then you can have the server program and the client program, or a few client tests programs on the same machine. Then you can test everything, and when your tests are okay, you can start deploying them on different machines, which will cost you a lot more work than having that on your local machines. We will see other uses of them. Not to be confused, the local host with private addresses. So there are 3 blocks of private addresses that are those that are given here. Typically, when you host a Windows machine, it will acquire an address that is in that range here. So those are the addresses you see most of the time when you're at home. Windows or Mac do the same here. Private means it's private, means it belongs to everyone. That's the opposite of private. But it means you're not supposed to see them in the internet. So if you're at home, you have your own set of routers. You can use whatever addresses you want from those private blocks. That's the intended use. If you're at home and you're not connected to the internet, and if you reuse the IBM addresses, for example, nothing bad will happen. You will, if you're completely disconnected from the rest of the world. But in practice, you're never really disconnected. You always have a way of connecting. So it's safer to use truly private addresses. When an internet router in the middle of the internet somewhere sees an IP packet with destination address, one of those addresses, it will drop it. It will say, that's not for me. I am a public internet, that's not for me. Why is that used? Well, this is typically used for home networks, also sometimes for Wi-Fi network. You're at home, you get a modem from Swisscom or Cablecom. This modem has one IP address from Swisscom or Cablecom, and then you want to connect all your gadgets, your smartphone, your PC, your printer, your TV, everything. You will need an IP address for each of those. So typically, those addresses, you will use them from the private network so that your operator does not manage this for you. Of course, that poses a problem. How do I access the public internet with private addresses? This is a major nightmare. That's called the NAT, that we will see later in a few more minutes. In addition to, for example, the EPFL Wi-Fi network, the public one uses the so-called EPFL public, uses a block of 10 addresses here. In the labs, we will often use those addresses because then we don't offend anyone by reusing addresses that come from another block. Not to be confused with the top ones is the so-called link local address. Link local means, here link means local area network. Link local address means an IP address that can be used only between systems that are on the same local area network. Again, it means a router will never forward to anybody who has such an address. Because if you're a router and you're forwarding a packet, that means you're sending something from one LAN to another LAN. Because if the two would be in the same LAN, they would not go through you. So either private or public, a router will never forward, unless you hacked it severely, a router will never forward a packet to such an address. It's called, therefore, link local, and this is this. Why is it used? Well, it's used if you are in an environment where you have no mechanism to allocate IP addresses. We see that in order to know which IP address you need to use an explicit allocation mechanism. Now, assume you're in the field, you have one printer, one PC, you want to print from your PC, you're not connected to anything else, we'll still need IP addresses for you and the printer because you use TCP-IP. If you use exotic protocols, I say you don't need that. If you use TCP-IP, you will need those IP addresses. So one way to get your IP addresses is to use those link local addresses. So you're sure that those addresses can only be used by people that are in the same local area network as you. Inside local area networks, people have become accustomed to use broadcast, which is a mechanism to send to everyone to detect whether such an address exists. So this is typically what you have if you are in an environment where there is no router connected to you. Then we have special addresses, multicast, so 224, all the addresses that start from that block, so 224 until practically the end, 239, those are multicast. Multicast is a very different animal. Multicast addresses are the addresses not of a machine, but of a group. So when you send to a multicast address, you send to a group. You don't know to whom you're sending. And in order to receive from that group, you will need to do something special. You will need to become a subscriber of the group. This is used, for example, for distribution of television over IP networks. This is also used in industrial, smart grid context also. We'll come back to that a bit later. This is not used in case we find a smart thing to do. And this specific address, which you recognize as only ones means broadcast, sent to everyone. Of course, you cannot send one IP packet to everyone in the world. That would be too easy for forging attacks, because you can do a denial of service attack by sending a few packets that will reach everyone. So this is a broadcast that is always link local, like those addresses. If you send a packet to this address, it will send to anybody that is on the same network as you, but the router will not forward it further, of course. Here is the IP packet format. So an IP packet is 20 bytes of header that contains and after the 20 bytes we have, for example, the TCP payload. The main parts of the header, so every line of this is here 4 bytes, a 32-bit word, and the main 2 parts are the source address and destination address. Then there is a zoo of other numbers that we will discuss a bit later. The only one that's relevant so far today is the protocol. So the field called protocol is a number that identifies what is contained inside the IP packet. Why do we need such a number? Because it's not always the same thing that's contained in an IP packet. We have seen 2 examples of things that can be contained in the IP packet. One is a TCP segment or a UDP datagram. So depending on whether we use TCP or UDP, then the thing will be different. Why do we need to signal here what's contained here? After all, if I send to you from a web server a video, I don't need to have a code inside the HTTP protocol that says I'm sending you a video. This is contained in the data itself with a header that's called a Mime Header. Here, we could imagine that whatever is contained here contains first something that says what it is. But this is not the way it's done. It's contained in the IP header itself. That's a general way of doing that we will find in every layer. Every layer usually contains some information saying what is the higher layer carrying. For example, the MAC layer, the Ethernet layer, has some information saying it is an IP packet that I'm carrying. Of course, the MAC layer is carrying only IP packets practically, but as we will see, not always. So the protocol types are, for example, TCP or UDP. There's another protocol type called ICMP, which is the error messages of the internet layer. So ICMP stands for Internet Control Messaging Protocol. It is all the error messages that have to do with the IP layer itself. What kind of error messages could occur? Well, for example, you might be sending a packet to a destination address that does not exist. So a router receives a packet, it analyzes its routing table, there is no match. If there are several matches, it will take the longest, but there might be no match. If there is no match, the router will say, I'm sorry, I have to discard the packet. If the router is a cooperating router, it will send an error message back to the source. Of course, you should not expect that Internet backbone router will do that, because it would be very easy to do denial of service attacks on routers, but enterprise networks could do that, for example. That's an example of an error message. There are other messages that we will see a bit later when we talk TTL in particular. That's for IPv4. Then there is IPv6. First, why do we have 2? Well, it's due to a bug in IPv4. There were 4 versions of IP that were all experimental, which minor details, until the final version, so-called final version, IPv4, that has 32 bits in the IP addresses. And then in the 90s, people started thinking, well, 32 bits, how many machines does that do? 2 to the power 32, 2 to the power 10 is roughly speaking 1,000, so 2 to the power 30 is 1 billion, 2 to the power 32 is 4 billions, that's 4 billion machines. At those times, people in the 70s, they said, oh, that's more than enough. By the time we have 4 billion computers, that's 1 computer per person. Now there are more people on the earth than in the 70s, twice as many almost. and more computers per person if we add the smartphones and the fact that there are multiple interfaces. So there's not enough IP addresses for everybody to have one. So in the 90s, people started saying, okay, let's address the problem, let's extend the address space. And then there were many, many different proposals, and they converged on a proposal that is very conservative, 128 bits. 128 is 4 times larger, but of course the address space is to the power 4. So the number of addresses we have is now astronomically large. People say it's the number of atoms in the universe. So we will probably have enough addresses. So some people say IPv6 is the true final version of IPv6. In 1,000 years, people will still be using IPv6. IPv6 was invented in the 90s. We are in 2015, and every year I say to you and the students, IPv6 is coming now. And it's, as we will see, it's not really coming. We need, for example, we don't have IPv6 on the wireless network of EPFL, so in order to do some of the labs, we had to set up our own Wi-Fi network, which is why you may have to go to INF019 to have IPv6 here. So that's a symptom. A place like EPFL, which is a research institution, doesn't see really any value or need to have IPv6. So it's part of the problems with IPv6 that we will discuss. There are lots of places in the world where they see value or need to have IPv6. There are the places where they don't have enough IPv4 addresses. But in Europe, everybody has one or several IPv4 addresses. As we will discuss, NATs are also part of the problem. They are making it possible to reuse several IPv4 addresses so that the same address is used by many machines, which is in principle impossible, but as we will see, is a divergence from the principle. When you extend the IP address from 4 bytes to 16 bytes, you have the nightmare of all programmers, which is how do I do a new version that was not anticipated when I did the first version. So you build a piece of software. If you're used to building software, you know the first principle of software, which is keep it simple. So you will do a little thing that works well, that works entirely and is simple. However, the limit of this principle is when you need to expand it, you may have to entirely redesign your system because your original system did not scale. So the principle of programming should be do it simple, but think that you will need to extend it. Here we have exactly this nightmare. An IP4 packet header has a place with 32 bits. Now we want to extend that. What do we do? We could use somewhere an extension that says, well, if there is 1 bit somewhere in the other place of the header, we add an option. That would mean, well, the rest of the address is out now in the option. Naively, I think, I was not involved in the discussion on IPv6, that's what I would have done. But there must have been good reasons for not doing this. Instead, they're saying, no, we don't want to manage these options, compatibility, etc. So they embraced another philosophy, which says, when you do some new thing, don't try hard to be compatible with the old because there will be a nightmare. It will ruin all your software. You will always need to do things to be compatible with the old. So do a new thing, and then things evolve so fast anyhow. After a few painful years, people will have forgotten the old. This is the Apple philosophy, right? If you have iOS, if you have an old iPhone, lots of things don't work. They don't support it, so you don't bother supporting the very old. Other companies like IBM and so on, they maintain the compatibility across everything, but that's a very different philosophy. And where's the truth? I don't know. But the fact is, for IPv6, they decided not to do an option in the IPv4 header or something, but to do a different packet format, which has a consequence that IPv4 and IPv6 are incompatible. If a machine that is an IPv4 machine and has not been upgraded to IPv6, receives an IPv6 packet, it will not know what to do with it. So it will not be able to handle it. Worse, if a machine has been upgraded to IPv6, but an application program has not been upgraded to IPv6, it will not be able to work with IPv6. Why is that? It seems like a contradiction. It seems like we're violating the principle of layers. And in some sense we are, but there is reality in the details of life that force things to be a bit different. Imagine you are writing an application program, like you will be doing in a few labs. You send packet to a client. Then at some point you will need to know the IP destination address of the client. Perhaps you will know its name. Then you go to DNS to resolve the name into an IP address. If you coded your program in a world where everything is only IPv4, of course, the field, the object, or whatever data structure you use, to carry this IP address will be an object of type IPv4. So now imagine the server runs only IPv6, then your program will not work, simply because you don't have the correct type for some things, for some objects that are the IP addresses. If you're smart enough, and we will teach you how to do that in the programming lab, you should code an object that works as well as for an IPv4 as for IPv6. But you will see it's much more complicated. So most people don't do that. Most code is not done to be IPv4, IPv6, except the very recent code, Internet Explorer, Safari, etc. They all work with IPv6, but they had to be recoded to work for IPv6. No big deal. Those things are recoded every week, so it doesn't matter. But the fact remains, those things are incompatible, which is illustrated here. If I have a web browser that speaks to a web server that is over IPv6 or to another web server that speaks over IPv4, the only way we have found to make this work is to have this web browser have an application that is aware of IPv6 and IPv4, and inside its machine, an IPv6 network layer and an IPv4 network layer. We call that a dual stack host. All modern operating systems are dual stack. Most of the time, IPv6 is not enabled if you run a TPFL, for example. But if you detect that you're in an IPv6 environment, this will be enabled. So this is what you have for modern equipment. All routers also have to be dual stack. So in fact, we have two internets. We have an IPv4 internet and an IPv6 internet. When you send a packet to a router, the router will see whether it's an IPv6 packet or an IPv4 packet, will apply its IPv4 routing table or its IPv6 routing table. They can be on the same machine, or they can be on two different machines. Remember what I said a few minutes ago. The concept of function is independent of the concept of machine. So you can have an IPv6 router, which is a physically separated box, or you can have a router that runs both IPv6 or IPv4. Both are possible. So this is how things are. Of course, there are good aspects to that. It makes things simple, because by having the two things separate, you can stop developing IPv4 and focus on IPv6, and you don't have to maintain compatibility. The route other than that, IPv6 is exactly like IPv4. That's the good news. Exactly, but things are long. So IPv6 addresses tend to be very long. Of course, they are 4 times more bit. They are written in this special form. They are written in hexadecimal, not like IPv4, because now hexadecimal has become more known, and you have calculators that can manipulate them. And this is, for example, an IPv6 address of EPFL, and here a private EPFL address. There are several IPv6 EPFL private blocks. One is for the smart grid, another one is for another research lab. A few rules for manipulating IPv6 addresses. IPv6 addresses are written by blocks of 16 bits in hexadecimal digits. One hexadecimal digit represents how many bits? 4. So one hexadecimal digit is exactly 4 bits. This is why we use hexa as opposed to decimal. And therefore, we need 4 hexadecimal characters to represent a block of 16 bits. So this is an EPFL address. Now, or not an EPFL, this is an address here. Now, if an address has lots of zeros, it's boring to write them, so we compress them by not writing them. We put the column between blocks, and an empty thing between two columns means zeros. Now, of course, if you have that in two places of your IP address, you don't know how many zeros are. So the rule is you can do it only once. Also, you can remove the leading zeros, as you do for when you write digits. For example, 0C26 can be written C26. Right? But the column here indicates me where I should put the zero. Those are the compression rules for IPv6 addresses. The IETF says when you write IPv6 addresses, you write hexadecimal digits, and you should write them in lowercase. Here are a few addresses. So the block that starts with 2000/3, that means the first 3 bits of this, which means anything in 2000 and 3000. I say 2000 and 3000 like everybody does, but it's not thousands, right? Those are hexadecimal strings that don't represent the number 2000. They are the normal IPv6 addresses. And here is some examples of them. We will use special ones like the 2002, 2002, it was invented in 2002, is the 624 IP addresses. Those are the ones we use in the INF 019. We'll come back to it later. There are special addresses that are derived from IPv4 addresses. But the EPFL addresses, in principle, are those ones. If you compare the IPv4 versus IPv6, you see a big difference. The IPFL block in IPv4 is 128.178/15. The ETH block is 129.130 or 132, don't remember. They are not contiguous. So if a router in California has a packet to send to EPFL or ETH, it sees them as 2 separate blocks. So the router needs an entry for each of those. So in all backbone routers of the world, there's one entry for EPFL, another one for ETH. We cannot aggregate the two because the blocks are not contiguous. In contrast, in IPv6, you see that the IP addresses of EPFL and ETH start with the same string, 200 and 620, which is in fact anything that is allocated to a customer of Switch. Switch is an internet service provider used by Swiss universities, which means that the router in California needs to have only one entry, 2001-620, for all of Swiss universities, instead of one per university or per block of the universities. That was one of the motivations also for having IPv6, is to reduce the number of entries that you have in the backbone routers. Today in IPv4 and the backbone routers, you have close to 500,000 entries. 500,000 means when a backbone router has one IP packet, it needs to do longest prefix match on a list of 500,000 for every packet it sends. That's the bottleneck in routers today. So people have invented special hardware just to do this function. The idea with IPv6 is perhaps we can relieve a bit of that by aggregating more, which we can because the address space is much larger. As with IPv4, there are special addresses. 0 is absence of address. 1, the address 1 is localhost. Then you have linked local addresses that are similar to the linked local addresses of IPv4, except the difference is that they are always used, whereas in IPv4 you use them only in the bad case where you are alone in the world, not connected to any router. In IPv6, as we will see a bit later, they are always used. In IPv6, there is the idea that the same interface can have several addresses, which is normally not the case in IPv4. Then you have also special prefixes for multicast, the FF, you have also the private addresses. Now, the private addresses in IPv6, the difference with IPv4 is that the address space is so large that it's typically possible to have a private numbering plan that mimics exactly the public numbering plan. So, for example, it's possible within EPFL that every machine has both a private and a public address. And you might be connected to only the private network of EPFL, or to both the public and private. And whenever you change, then you can keep the same host part of the address, which is not possible in IPv4. In IPv4, if you're on the private part of the network, you have a 10 dot something address. Right. The IPv6 packet format is, of course, a bit different. It's much longer because the addresses are longer. So now you have 32 bytes of addresses. So the IPv6 address is now 40 bytes. So if you send one ping with IPv6, it costs already 40 bytes just for the header. There is also similarly a protocol type, which is called next header, but which otherwise is the same as we saw before. A quick checkpoint on your ability to translate from hexadecimal to dotted notation. Here is a non-standard way of writing an IPv4 address that we will find more and more. In particular, there are cases that we will see where you want to put an IPv4 address inside an IPv6 address. Then if you do it, you will write it in hexadecimal. What is the dotted decimal notation? The standard address for this string, 80C1FFFF. You don't need a calculator. That's an exercise I would like you to do without checking your calculator. I close the poll now. And of course, it can be only the first one. Congratulations. This cannot work because 393 is, of course, larger than any possible address. Wonderful. We have seen so far the principles of IP. Now let's see our first deviation from principle. We'll see a few others. NATs, which stand for Network Address Translation, was invented to satisfy the problem of scarcity of IP addresses. Normally, when you get from Swisscom an internet service, Swisscom should give you a block of addresses. They should tell you, okay, I give you 192, 200, 300, /24. And then you have 256 addresses that you can use for your 256 machines or interfaces in your house. Swisscom doesn't do that for several reasons. First, they are greedy, so they sell you one address. If you want 2, you will pay twice the price of one address. If you want 10, you will pay more than for, perhaps not 10 times, so you will pay more. So they see addresses as something they can sell. So you will have to pay. Second, there's a scarcity of IPv4 addresses because we don't have enough. So there's a lot of pressure everywhere in the world to not give too many addresses to anyone. So apart from greed, that's a good reason for not giving you more than one IP address. The problem was solved by hacking a system which says, I will make a box, that's called a NAT, that will allow me to do this miracle. Here's the address that Swisscom gave me, and I have only this one. Then I will be able to have, of course, if I have only one computer, that's okay. Instead of connecting my ADSL modem, I connect directly my computer, and then I have only this address. Things are fine. You have more than one computer, I will have a problem. Here I have two. Then what I will do is, at home, I will use private addresses. I'm allowed to do that. Nobody will complain that I'm using their addresses. And then we have a problem. We have a problem that if I am now contacting a web server somewhere in the world, the source, if we follow the principles, this box should be a router. So it will put a source address, my address here, and then it will go to a web server, but the web server will see the destination address is a private address. I don't know what to do with it. Rightfully so, because there are probably millions of people that have the same address as me. So the web server doesn't know where to send to this address. So it doesn't work. Of course, if we violate the architecture, we need to violate it at least twice. If we violate just one, it stupidly doesn't work. So you need to do another thing to compensate this. This other thing is the NAT. What does the NAT do? Well, as the name says, it will translate the IP address, which a router normally never does. Remember, a router is the principle of the post office and the postcard. You have the IP destination address, you look at it, you send it forward, but you don't change it. Here you will change it. That's called a network address translation. A network address translation is fairly easy, except now that we still have a problem. How can I change the address and still make it possible that two computers use the same address? There is this principle of drawers. I mean, if I have to do a mapping, I need as many addresses on the left as on the right. So I have a problem. And the problem, in principle, is unfeasible. It's unfeasible if you stay in the IP layer. So you need to go out of the box to solve it. The way this is done is by looking in the TCP and UDP headers, which of course violates everything. I mean, an intermediate system should not look at what's inside the packet. That's against the principle of packet switching. Inside the IP, the TCP or UDP header, there is a number that is called a port that we will see a bit later, but you're sure you're familiar with that. Port number is an indicator of which process is listening to what. For example, all HTTP servers, in principle, are listening to port 80. So when you send to a port 80, it means it should go to an HTTP server. And similarly, the clients, when you call the socket interface, you have to give a port number to which you will associate this socket. So there is a port number in the packets, and then the NAT does address translation and does exact matching from its table, in the sense that, for example, when the NAT has to send a packet from a local machine that has this private address with UDP port 1029, for example, this might be a DNS request sent by this machine, or 11 by this one, by machine B. When it sends the request over the internet, it has to change the IP address. So it will change the source IP address to which address can it use? Well, it can use only this one. That's the only address that will allow me to receive the response back. So I will put as source address this one instead of that one. Okay? But of course, there is a bug in this slide. It is 0 here. Of course, if I do this and keep and do nothing else, then if A and B are both sending from DNS resolvers are sending requests to some server in the world, then they will be mapped to the same address here. So there will be a problem when the packet has to come back. I will not know whether this packet has to go to A or B. So the trick is to fiddle with the port numbers. So this NAT sees a packet, source address, protocol type UDP, source port number 1029. What it will do is forge the source address, make this address, protocol type UDP, and then it will also change the port number. It will pick whatever port number has not been used, is not available in the table, in this case 3441. And then when this other machine sends with exactly the same port number, it will need to map it to a different port number. And it has to remember that. So the NAT, when you send your DNS query, on the fly, will choose a port number for you that it will masquerade, and will keep it in its table, so that when the reply will come from the DNS server, the DNS reply will come to that destination address and to this destination port number. So the DNS server has the illusion that it has one machine with several processes, several programs inside the machine that are sending DNS queries to it. The same source address, but different port numbers, which is what happens if you have different programs that use the socket interface. Voilà, that's all for today. See you tomorrow.